Welcome to these NPTEL lectures on dynamics and control of mechanical systems. In this week, we are looking at classical control approaches. In the last lecture, I had discussed the root locus approach. In this lecture, we will look at the frequency domain approach. My name is Ashitava Ghoshal. I am a professor at the Department of Mechanical Engineering in the Center for Product Design and Manufacturing, and also in the Robert Bosch Center for Cyber-Physical Systems, Indian Institute of Science, Bangalore. So in the last lecture of this week, we will look at frequency domain approaches. Introduction. Frequency response of a dynamical systems were developed by Nyquist, Bode and Nichols and many others in the 1930s and 40s. For a linear system, the steady state output to a sinusoidal input is of the same frequency as the input. So this is a property of a linear system. The output amplitude and phase is a function of the input frequency. The input frequency can be varied in a range, and the output amplitude and phase is measured in this frequency domain approach. It is very popular with practicing engineers because it is very easy to excite a system with varying frequencies and experimentally measuring the output. So if anybody has done some experiments with vibration, you can put your system on some kind of a vibration shaker, and then you can excite the system at different frequencies, and then you can measure the output, okay, both amplitude and something called phase, which we will see very soon. So measurement of the amplitude and phase can be directly used to obtain a system model and then can be used for design of a controller. So this is why it is very popular with practicing engineers. Frequency domain approach provide a good design tool in the face of uncertainty in the plant. In the last week, we had looked at S domain or the root locus, whereas here it is very easy to see what is the frequency content of the system or how the system responds to a sinusoidal input. Whereas in the root locus, it is a little bit more involved. We need to find the root locus, and then if you really want to find out what are some of the responses of the system, we need to give some step input, and then we have to find the inverse Laplace transform and so on, and then look at the response of the system. In the frequency domain, where it is much more easier. So for a dynamical system with a transfer function g of s, if you give an input which is unity, which is x of t as sine omega t, the output y of t is a sine omega t plus phi. So if you look at the Laplace transform of g of s, if you look at the Laplace transform of the input x of t, which is given by x of s, and the output which is y of s, from Laplace transform we know that y of s is given by g of s into x of s. Okay, so x of s and y of s are the Laplace transforms of x of t and y of t. The steady state response to a unit amplitude sinusoidal input, basically it is 1 into sine omega t, so it is denoted by g of j omega, and it can be written as a of omega into e to the power j phi of omega. So e to the power j phi is nothing but like cos phi plus I sine phi. Okay, and both this phase phi as well as the amplitude is a function of the input omega, okay, input frequency of the excitation. So the magnitude of this j omega can be obtained, and this is called the amplitude, which is a function of omega, and the phase of the output is the angle of gj omega, and that can be obtained from this formula, which is tan inverse of the imaginary part of Gj omega and the real part of Gj omega. So if you were to expand G of j omega, you can see that you will get one which is something like cos phi, which is the real part, and then you'll have something which is I sin phi, which is the imaginary part. So from the real part of this and the imaginary part of this, we can find the angle. It is very straightforward. This is basically how cos phi and sin phi, so tan inverse of imaginary part, which is sin phi, divided by cos phi is tan phi, so we can find phi. So in the steady state, if we are giving an unit amplitude sinusoidal input, we can obtain the amplitude of the output, and we can also obtain the phase of the output. So this is the same thing as y of t is a sine omega t plus phi. So we can obtain the a and phi. Remember, for a linear system, if the input frequency is omega, the output frequency is also omega. If x of t is not of unit amplitude, it is not x sine omega t, but let's say some 2 or 3 sine omega t, then the magnitude of g of j omega and the phase angle are amplitude ratios. Okay, and the phase shift of the output sinusoid with respect to the input sinusoid. So basically now instead of unit amplitude input, we get some y. If you give some non-unit amplitude, we will get the output will be a ratio of the output amplitude by the unit amplitude, input amplitude. So to obtain magnitude of Gj omega and the angle from the transfer function, it is very simple. We just substitute S equals j omega. So in some sense, the transfer function which was obtained using Laplace transform, if I want to find the amplitude and the phase, then all we do is substitute S as j omega, j is square root of minus 1. And then what we can do is we can obtain the magnitude of j omega. Okay, and in particular, we can plot the magnitude in various ways. So if you use a logarithmic plot of the magnitude with respect to omega, this is called as the Bode plot. If you plot this magnitude or Gj omega as a polar plot, then this is called as the Nyquist plot. And if you use log magnitude versus phase, this is called the Nichols plot. In this lecture, we will look at Bode plot. If anybody is interested in Nyquist plot and Nichols plot, then we need to go and see some other textbook. But it is very basic. It is basically again coming from this g of j omega, and you plot it in different ways. You plot both magnitude and phase in different ways. In the Bode plot, we will plot the logarithmic of this magnitude with respect to omega and phase with respect to omega. If the input is periodic with many frequency component, most likely any signal or any excitation need not be of a single omega. It could be a combination of various omegas. So in that case, we can use Fourier series. So we can use Fourier series to obtain the frequencies in the input, and then for the output, we can obtain the frequencies for each one of those input omegas. So it's a very, very powerful technique. So we know what is the output amplitude and the phase when we give a single omega. If you have a broadband signal or a broadband excitation with many frequencies, then we do the Fourier series of the input and we find out all the various input frequencies, and then we can use the same technique to find the amplitude and phase for the different input frequencies. So let's continue. In this lecture, we will look at Bode plots. The Bode plot was developed by Bode at Bell Labs in 1930s. So it's a very nice, quick and accurate plotting for systems response, and it can be used for design of controllers. So if you have systems in series, so G of S is actually a product of G1 of S, G2 of S and all the way to, let's say, gk of S. So it's a product of various transfer functions 1 through k. The phase angle of g of S is nothing but the addition of the phase angles of each one of them. Okay, so remember e to the power j phi. So if you have products, so e to the power j phi 1 plus j phi 2 and so on. So the total phase angle will be nothing but the summation of each one of these phase angles obtained from g1, g2 and so on. The magnitude is the product of the magnitudes. So the magnitude of g of S will be the magnitude of g1, the magnitude of g2 and so on. So Bode decided to plot the magnitude on a log scale, so with base 10. So if you were to plot the magnitude on a log scale in base 10, so basically what is happening is this product will become addition. So log of A into B is basically log A plus log B. And he also decided to plot using decibels. So he was working in Bell Labs, and in communication field, a decibel is a very common term or a common way of measuring this magnitude of a signal. So, and what is a decibel? It is nothing but 20 log of g j omega. So we will plot the magnitude in decibels, which is 20 log g j omega versus omega. So later on I will show you in MATLAB we can plot the magnitude directly, or we can also plot the magnitude in decibels. The phase is also plotted in degrees versus log omega. So both x-axis for magnitude and phase, okay, we plot versus log omega. And this has some advantages which we will see shortly. And these magnitude and phase of g of j omega can be plotted graphically using asymptotes and smooth continuation between asymptotes. So it is very, very easy to plot, especially the magnitude, because we can see that the magnitude of in log scale is magnitude of this plus magnitude of this, and so we can sort of keep on plotting separately for each one of these transfer functions, g1, g2 and so on, and then we can smoothly connect all these various pieces, and then we can get the magnitude of the complete system. And the magnitude and phase is typically plotted one below the other for better understanding of the system. And again, we will see this later in some examples. There are three main types of terms in a Bode plot. So the first one is gain with integral or derivative term. So we can have some constant k, and then we can have j omega. So if n is negative, then it will be like k divided by s. So that is an integral term. If n is positive, then you have k into s. And if n is 1, so then it is like k divided by s. If n is 2, then it is k divided by s square. Okay, so this n and k will give you both derivative terms and integral terms. We can also have what are called as first order terms, which is nothing but j omega tau plus s. Okay, and this could be also to the power plus or minus 1. So if it is plus, then it is the numerator. If it is minus, it is 1 divided by j omega plus tau plus 1. So remember, j omega is coming from the s. So this is like 1 plus s into tau. So this is like a pole. Okay, whereas if it is in the numerator, it is like a 0. We can also have quadratic terms, which are like 1 plus 2 psi, again j omega divided by omega n, plus j omega divided by omega n square. Again, this could be in the numerator, then this will have an exponent of plus 1, and if it is in the denominator, it will be minus 1. So it is very similar to omega n square divided by s square plus 2 psi omega ns plus omega n square. So remember, in root locus we could see that there were these quadratic terms, and again s is substituted by j omega, and we can simplify and we can rewrite those quadratic terms in this form, either in the numerator or in the denominator. Any higher order term, let's say we have something like s plus 3 plus something cube or even fourth power or higher power, they can always be factorized. So any polynomial in s of higher order than quadratic can be always written in terms of quadratic terms and linear terms and constant terms. Okay, so if not analytically, we can always do it numerically. So let us see what are the Bode plots for some of these terms. So I want to plot log of k magnitude of j omega n. So this, because it's log of this, can be written as log k plus n log j omega magnitude. Okay, so the magnitude plot is a straight line. You can see that the magnitude of this k j omega is nothing but a straight line with a slope n. Okay, so if n is equal to 1, then we will have 20 dB per decade. So basically, if omega goes from 1 to 10, the magnitude will increase by 20 dB per decade. So decade here means in the log scale you have 1, 10, 100 and so on along the x-axis, and every decade the magnitude increases by 20 dB. If n is minus 1, then it decreases by 20 dB per decade and decreasing with omega. The phase angle is given by the tan inverse of the imaginary part divided by the real part. In this case, the phase angle is 90 degrees. Okay, so because it is, and depending on n, we can have either 90 into 1 if n is equal to 1, or depending on n of 2, we will have 180 degrees and so on. So the phase of j omega to the power n is n into 90 degrees, and it is independent of omega. Okay, hence it is a horizontal line. So if n equals minus 1, the phase angle is minus 90 degrees. If n equals plus 1, the phase angle is plus 90 degrees. And these are plotted here. So this is the plot of phase, sorry, this is the plot of magnitude versus the frequency. So what you can see here, the x-axis, the frequency is in the log scale. The y-axis, you have the magnitude, and MATLAB also tells you what is the magnitude in dB. So basically this is the magnitude, and this is 20 times that number. So you can see here 10 to the power 1. So this is here 20. Okay, so magnitude in dB is 20 log of this. So we can plot the magnitude of g of j omega. So if it is s, which means what? N is plus 1. So then we'll get a plot in which the slope is increasing by 20 dB per decade. So you can see from minus here, which is 10 to the power minus 1 to 10 to the power 0. So this is 1 decade, and it goes from minus 20 to 0. So the slope is increasing at 20 dB per decade. Okay, likewise, if it is g of s is 1 over s, okay, so it's like an integrator, then it is decreasing at 20 dB per decade. Okay, so here you can see it is 10 to the power 0 is some point here, and in the next decade it falls by 20 dB. Okay, and if it is 1 of s square, that n is equal to 2, and in the numerator, then it will increase at 40 dB per decade, which is what this line shows. The phase, as I have mentioned, is a constant. Okay, it will be 90 or n into 90, and depending on whether n is positive or negative, we will have plus 90 or minus 90 or minus 180 and so on. So in this example, when g of s is s, so then it is at 90 degrees. So this is the plot which is between 50 and 100, it is 90 degrees. And it is a constant line with respect to the frequency. If it is 1 over s, that means since it's in the denominator, then it is at minus 90. So this is here. And if it is s square, then it is 180 degrees. Okay, so then it is here. So these plots are obtained using MATLAB. Okay, so MATLAB has all these tools which, given the transfer function g of s, it will plot you the magnitude and the phase in log scale. If it is a first order term, which is like j omega tau plus 1, so it is like in some sense 1 into s divided by s plus a, or numerator it is like s plus a. So then the magnitude for j omega tau much less than 1 is approximately 1. So you can see the magnitude of this is j omega tau plus 1, and if this j omega tau is much less than 1, the magnitude is 1. If j omega tau is much greater than 1, then the magnitude is j omega tau. So omega equals 1 by tau is called as a breakpoint, and there are these two asymptotes which cross at the breakpoint. So asymptotes means in these two ranges. In one case it is much less than 1, and in the other case it is much greater than 1. So these are the two asymptotes, and I will show you a plot soon. At the breakpoint, the curve is little bit higher or lower, and this is, we can compute actually accurately, and it is 3 dBs above if this j omega tau plus 1 is in the numerator, and 3 dB below from j omega tau plus 1 to the power minus 1 if this first order term is in the denominator. So this is how the magnitude looks like. So we have one part which is this asymptote which is constant. So this is like 1, 10 to the power 0 is 1, and the other part is, it is like j omega tau. So as omega increases, it increases at some angle. Okay, and at the break point, which is at omega, the output is a little bit more if it is in the numerator, and I'm not showing you the plot when it is in the denominator, but this asymptote or this red curve, which is the magnitude versus frequency, will be slightly lower, 3 dB lower. And these plots have been obtained for tau equals 1. Okay, that is how you get this frequency. The corner frequency, or the frequency at which this two asymptotes meet, is 10 to the power 0, which is 1. Okay. We can also plot the phase of this first order term. So again, the phase angle when j omega tau much less than 1 is 0. Okay, and when j omega tau is much greater than 1, it is 90 degrees. And when j omega tau is very close to 1, the phase angle is 45 degrees. Phase angle, remember, is tan inverse of imaginary part divided by the real part. So if you plot phase versus frequency, again omega, so there is a part which is at 0, there is a part which is at 90, and in between there is a line which is at 45 degrees. Okay, and this curve is a smooth continuation from here to here. So it is not as if it is discrete at this. So these dotted lines are the asymptotes, and the actual phase plot when j omega tau plus 1 is in the numerator is given in this form. If j omega tau plus 1 was in the denominator, then the slope will be in the opposite direction. So the actual curve is smooth from 0 to 90 degrees, and it will pass through 45 degrees. So it is here, somewhere here, it is 45 degrees. At the break point, it is at 45 degrees. And well below this frequency, it is 0, and well above, it is 90 degrees. The second order term is a little bit more interesting. So we can have a second order term which is of the form 1 plus 2 psi j omega divided by omega n plus j omega divided by omega n whole square, and it could be in the numerator, in that case it is plus 1, and it could be in the denominator, in which case it is minus 1. So the break point here is omega equals omega n, and the magnitude changes by plus minus 40 dBs per decade. So if it is in the denominator, it is minus 40 dB per decade. Okay, so the minus sign corresponds to if the second order term is in the denominator, and plus if it is in the numerator. So unlike the first order term, which was 20 dBs per decade, here it is 40 dBs per decade. And we can plot again the magnitude of Gj omega. MATLAB will give you both magnitude as well as the magnitude in dB. Okay, these plots were all obtained using MATLAB. So for different damping psi, we'll get these different plots. So if it is more than 0.7, then there is no amplitude, there is no amplification. If damping is small, so for example psi is 0.1, then the amplitude is 1 for a while, and then near the frequency omega n, in this case again tau is omega n is 1, you will get an amplification, and after this amplification it will be minus 20 or minus 40 dB per decade. Okay, so you can see from here, which is 10 to the power 0, and then at 10 frequency of 10 radians per second, from here to here it drops down from 0 to minus 40. Okay, so the minus sign is because we are plotting when this second order term is in the denominator. So for different psi, so psi equals 0.2, the plot is different. So the amplification at the corner frequency is smaller when the damping is more, and beyond some damping, which is roughly 0.7, you can see that there is no amplification. So the plot of magnitude is always below this 10 to the power 0 or 1. At the break point, the curve is above or below by an amount which depends on psi. So in this case, it was not like 3 dB every time. Okay, here it will be different value above or below depending on the value of psi, and there are no real simple rules to sketch what is happening here. We know what is happening before and we know what is happening afterwards. This is minus 40 dB per decade, but near this break point you need to actually calculate, and we need to be careful and compute correctly. The phase plot is also slightly different. Okay, so the phase plot for the second order term looks like this. So well below this corner frequency or break point, it is 0, and the phase angle after much greater than this omega n, it is now minus 180. It is not minus 90. Okay, again we are assuming that this is in the denominator, and near this break point again, depending on the phase, depending on the damping, you will get different phase plots. So there is a difference here when psi is 0.1 or psi is 1. Okay, so if psi is 1, it looks like this. When psi is 0.1, it is higher. Okay, so again there is no simple rule for sketching at the break point. You need to actually compute this phase angle. We can always compute, which is tan inverse of imaginary part divided by the real part, and then we can plot. But the basic idea is below this breakpoint it is 0, and above this breakpoint it is minus 180. So as I said, the breakpoint is at omega equals omega n, and the phase changes by plus minus 180 degrees. So if it is in the numerator, then the plot will be 0 to 180 above, and this plot is when it is minus, so it is going down. Now let us look at a composite plot. Okay, so suppose somebody gave you a transfer function which is g of s is s plus 0, 0, 1. We have taken these numbers arbitrarily, divided by s into s plus 10 into s squared plus 2s plus 2. So we have a first order term, we have one integrator, then there is another first order term in the denominator and a quadratic term. And I want to plot the magnitude and phase of this composite g of s, which contains various terms. So, and Bode plot is very sort of easier to do. Okay, so what we can do is we can first convert this s to g of j omega. So substitute s equals j omega, and then we can simplify this, and then we can rewrite this transfer function as g of j omega equals 5 into 10 power minus 4. The numerator will be j omega divided by 0.01 plus 1. So you can roughly see where it is coming from. S equals j omega, and then we divide by 0.01 so that we have this plus 1. Because the standard form in Bode plots, it is like this. So you have j omega tau plus 1. So in this case, tau is 1 divided by 0.01. Likewise, we can obtain s is j omega here. This s plus 10 will become j omega divided by 10 plus 1. And this quadratic term will become 1 plus j omega squared divided by 2. So first step is to convert from g of s, which is the Laplace transform, into this g of j omega. Okay, and then we can plot individual terms. Remember, g of j omega, if it is a product of g1, g2, g3 and so on, then we can look at each one of those g1, g2, g3 separately, and then we can plot each one of them and then sort of smoothly continue. Okay, connect each one of these parts of the magnitude and phase plots. So the first term is 5 into 10 minus 4 divided by j omega. So this is like k divided by s. Okay, so then we can see that the magnitude plot looks like this. Okay, so it is decreasing because it is in the denominator, and the phase is constant, which is at minus 90 degrees. So we can plot for the first term, which is 5 into 10 minus 4 divided by j omega, as a magnitude and a phase, and we can plot one below the other with the same x-axis, which is the frequency. In this case, it is the magnitude. MATLAB also gives you the magnitude in dB, so we can see what is the magnitude in dB also. And the phase is minus 90 degrees. So this is the standard form for a transfer function, which is, k divided by s, something like g of j omega and k divided by j omega. We can next look at the effect of the first term, first order term. So we can plot what is g of j omega, which is now 5 into 10 minus 4 divided by j omega, which was earlier, and then we'll plot what is happening due to this first order term, which is j omega divided by 0.01 plus 1. So what you can see is we have a corner frequency or a breakpoint at this point. This part was this magnitude, and then it is like this because now it is going up. Okay, so the effective thing will be this, and the phase will look like this. So it starts from minus 90 and then it goes to 0, and in between we have this 0.01, so which is this 10 minus 2, this is the frequency in radians per second. That is where the change is happening. And these are the asymptotes. The dotted lines are the asymptotes. Now let us look at what happens when we add the second order term. So then we have this one part here, but the second order term is in the denominator, and the second order term, the magnitude goes as minus 40 dB per decade. Okay, so we can again find a breakpoint which is here, and then we can plot the magnitude. So the total of these 5 into 10 minus 4 j divided by j omega, the first order term and the second order term, we will have a magnitude plot which looks like this is the first part, second part, and third part. Okay, and the phase is also now a little bit more complicated, but we can keep on plotting at what is happening to the phase and magnitude at the different breakpoints. Okay, and again the dotted lines here are the asymptotes. And MATLAB can be used very easily to plot the phase and magnitude of a system or a g of j omega given in this form. And finally, we can show what is the total Bode plot for the system, which is 5 into 10 minus 4. There is a numerator, there is a j omega in the denominator, there is j omega by 10 plus 1 and a quadratic term. So again, we can plot that there is one part here, there is one breakpoint here, there is another breakpoint here, then there is another breakpoint here, and we can plot all these asymptotes, and then we can plot this smoothly, the magnitude plots. The phase plot also can be plotted, so it goes from, this is minus 90, it goes almost up to 0, the asymptote is at 0, then it can go up to minus 270. Okay. And again, this magnitude and phase plots can be very easily done. Remember, it is log magnitude, so hence it is like pieces of it, and we need to plot each piece and then smoothly connect each piece. Let us look at the root locus of this same system or same transfer function. So in the case of root locus, we have g of s, which is s plus 0.01 divided by this. Okay, so what you can see is there are these poles which is at s equals 0, then there is a pole which is at s equals minus 10, and then there are these two imaginary poles, okay, complex conjugate poles. There is also a 0 which is at 0.01. So here this part is magnified, and you can see that there is a part of this root locus which is going from this pole to this 0, and then there is one more branch which is going from minus 10 to the left, and then there are these two imaginary poles from where the two root locus will go off to infinity. So again, we can plot this using MATLAB. So the question is, this is what you obtain from root locus, and previous plot I showed you what you obtain from magnitude and phase. So the question is, which one is better? So most engineers find the phase magnitude plot, okay, or magnitude phase plot with respect to omega easier. Here also we can obtain some interesting things. We can see that for some gain it crosses the imaginary axis and it becomes unstable. Okay, but the plotting of this is not that simple. For the Bode plot, it is basically pieces and then you connect it smoothly. The Bode plot also gives you what is called as gain and phase margin. And let's just go over this notion of a gain and phase margin. A system is neutrally stable when the root locus is on the imaginary axis, right? And this corresponds to k of magnitude of k g j omega as 1. and with a phase angle of 180 degrees. A system is stable if the magnitude of this k into gj omega is less than 1 at the angle 180 degrees, when the phase angle is 180 degrees. The gain margin is defined as the factor by which the gain is less than the critical value. Okay. The gain margin indicates how much the gain k can be increased before instability happens, before this magnitude goes more than 1. The phase margin is the amount by which the phase of gj omega exceeds 180. Remember, when it is neutrally stable, the magnitude is 1 and the phase angle is 180 degrees. If it is stable, the magnitude is less than 1 and the angle is 180 degrees. And if it is unstable, then this magnitude will be greater than 1. Okay, so the question is, how much can we increase this k, okay, such that it still stays k of gj omega is less than 1. And the phase margin is amount by which the phase of gj omega exceeds 180 degrees, okay, when this magnitude is equal to 1. So the thumb rule is, if the phase margin is above 30 degrees, okay, then it is a robust system. So this is obtained by engineers. So they will design a system, a control system, such that the phase margin is at least 30 degrees. Okay, when the magnitude of this k gj omega is 1. So let us look at an example again, and we will look at it both in terms of root locus as well as Bode plots. So the example is a very simple one, which is g of s is given by 1 divided by s into s plus 1 whole square. So this is the dynamical system, which is 1 divided by s into s plus 1 whole square. We have a controller k, and again there is an output y, there is a reference input r of s. So the error is rs minus ys. So we can obtain the root locus of this system, and the root locus looks like this. So there is a pole, open loop pole at s equals 0. There is 2 open loop poles at s equals minus 1, and as k increases, one branch goes off to infinity towards the left, one more branch goes towards this, and another one comes towards this. They meet at a point and then they diverge and go off to infinity in this direction. So this is the root locus, and you can find that this root locus will intersect the I omega or the imaginary axis in the s plane at k equals 2. So k equals 2 is a neutrally stable state for this transfer function. So let us now look at the same thing using Bode plots. So we have the plot of k gj omega and the phase margin with respect to omega. So what you can see is, for k equals 0.1, this is the blue plot. So you will get one plot here. So there is one corner frequency, or there is a breakpoint here. There is another breakpoint at here, and there is a third breakpoint here. And we are plotting this magnitude again using from these 3 parts. So there is one by s, which is like k divided by gj omega. Then there is one which is 1 by s plus 1 or something like that. And then there is one which is 1 by s plus 1 whole square. So you can do partial fractions of this. So we will get a plot of magnitude when k is 0.1, which is this blue line. Then if k is 2.0, which is this, remember k equals 2.0 is neutrally stable, and k greater than 2.0 it is unstable, and k less than 2.0 it is stable. So let us see what is happening to the magnitude and phase for k equals 0.1, 2.0 and 10. We have chosen these 3 k's value sort of arbitrarily. So what you can see is at k equals 0.1, the phase margin is about 180 degrees. This is 100. So remember, it should be minus 180 degrees, but the actual phase is about minus 100. So there is a phase margin of 80 degrees. So it is very, very stable and robust. Whereas when it is at neutral stability, which is at this point k equals 2, you can see that the phase margin is minus 180 degrees. Okay, so there is no phase margin here. Whereas when it is unstable, which is k equals 10, then you can see that the phase margin is minus 35 degrees. So basically there is a negative phase margin, which means it is unstable. So this is what is mentioned here. At k equals 0.1, it is stable with a phase margin of 80 degrees. It is very good. Remember, the thumb rule is it should be at least 30 degrees. At k equals 2.0, it is neutrally stable with a phase margin of 0. And k equals 10, it's unstable with a phase margin of minus 35. So in summary, the frequency domain approach involves obtaining the steady state performance of a system to a sinusoidal input. It is very simple, or at least fairly simple, to generate experimentally and plot magnitude and phase from measurements. From the Bode plot, one can get good insight into the system and its stability. If the phase margin is more than 30 degrees, then it is robust and it is stable. There are also other frequency domain approaches. For example, you can have Nyquist and Nichols. So remember, Nyquist plot is a polar plot of magnitude and phase, whereas Nichols is log magnitude versus phase. So these have also been used, and you can find it in various textbooks where classical control techniques are used. So we will not go into this, but the basic idea is, again, by looking at the magnitude and phase to a sinusoidal input, we can get good insight into the performance of the system. The steady state response to sinusoidal input is basically what we get. It is not really related to the transient response, and frequency response is only indirectly related to the transient response. So except for second order systems, we cannot say much about the transient response of a system from the Bode plot. Okay, whereas remember, in state space approach, we could very easily say what is the transient response. Similarly, in root locus, for second order system, we could find what is the transient response, peak overshoot, settling time, and all those things could be found out. Whereas in Bode plots, it is not that easy for any higher order system.